Good day. What we're going to look at today are minerals and mineral identification. Well, let's start with what is a mineral. Well, a mineral, by definition, is a naturally occurring inorganic crystalline solid with characteristic physical properties and a narrowly defined chemical composition. Minerals are what make up our rocks. Rocks are defined as an aggregate of one or more minerals. Well, what we're going to look at today are the physical properties of the minerals. These physical properties are going to be what helps us identify each of the individual minerals. So let's get started with what are those physical properties. Well, those physical properties are going to be things like color and luster, hardness, crystal form, cleavage, fracture, streak color, specific gravity, along with a few other special properties that a few of our minerals have. So let's start off with color. Color is going to be a visual quality of a mineral that results from the way they absorb or transmit the light. Color can be a useful indicator of a specific mineral. For example, potassium feldspar. Potassium feldspars are always going to be some shade of pink. However, with some minerals, color is not a great indicator. Color can be varied in some minerals. For example, quartz. Up here on the screen, we see several different versions of quartz. We see a yellow quartz, which is referred to as citrin. We see a white or clear quartz just below the citrin. We also see a smoky quartz, which is a smoky brown color, and even a purple quartz up here, which is referred to as amethyst. When it comes to quartz, color is not a good indicator, but it's still, even if color may or may not be a good indicator, it should still be recorded when looking at a sample. Next would be luster. Well, luster is the quality and intensity of light reflected from a mineral and is characterized as metallic, submetallic, or non-metallic. When we're looking at luster, it's how the light is reflected from a fresh surface of a mineral. Is that fresh surface reflecting back to us a color that looks or appears to be metallic in nature, like gold or silver? If we look at the image up here in the corner, we see galena and pyrite. Well, galena and pyrite both show up as a silver and a gold color. This would be referred to as a metallic luster. Down below, we have an image of gypsum. The gypsum is reflecting the light back to us, and it is shiny, but it's not metallic. And it's very important that you don't confuse shiny with metallic. The next physical characteristic that we would look at is hardness. Hardness is a mineral's resistance to abrasion or scratching. With any mineral, we put it on a scale from a 1 to a 10. This is referred to as Mohs hardness scale. If we look over here to the left, we see an example of Mohs hardness scale. On Mohs hardness scale, we use 10 separate minerals to identify with these particular hardnesses. One would be talc. Talc would be the softest. Talc, if you've ever come across it, you can actually dig your fingernails down into it. It's very, very soft. 10 would be a diamond, being the hardest substance. Also on here are a few common objects that we might use to test hardness. The first one being your fingernail. Your fingernail is approximately a 2.5. Then we would move up to a copper penny, which is a 3, and then a glass plate at a 5.5 to a 6, depending on the glass. Well, if we were to attempt to identify hardness, what we would do is use some of these items to test the hardness or test its resistance to abrasion or scratching. We always start with the softest item, which would be our fingernails. Our fingernails are approximately a 2.5. What we would do is take the sample and attempt to scratch it with our fingernails. If our fingernails did scratch the object, then we would have a substance that is either a 2.5 or less, and we would record it. However, if our fingernails didn't work in scratching, we would move on to a penny. A penny has a hardness of approximately a 3. What we would do is attempt to scratch the mineral with the penny. If the penny scratched, then we would have a range for the hardness. We wouldn't know the exact hardness, but we would have a range. We'd know it's somewhere between that 2.5 for a fingernail and a 3 for a penny. If the penny will not scratch, we would move on to the next object, which would be a nail. Well, a nail has a hardness of approximately a 5, a steel nail. We would try to scratch the sample with the steel nail. If this worked, then we would have a range of a 3 to a 5, the penny to the nail. If the nail does not scratch, we would move on to a glass plate. Now remember, glass plate is approximately a 5.5 to a 6. We would, with a glass plate, because we have the potential for doing harm to ourselves by holding the glass plate in our hand, we're going to reverse the process. Instead of attempting to scratch the mineral with the glass plate, we're going to attempt to scratch the glass plate with the mineral. Place the glass plate firmly on the table with your fingers holding the glass plate to the table. Take your sample and attempt to scratch the glass plate. If the mineral scratches the glass plate, then we know that we have a mineral that is either at least as hard as the glass or harder. So we would say it's somewhere around a 5.5 or greater. If it will not scratch the glass plate, then we will say it's somewhere between a 5 and a 5.5 and move on. The next item is crystal form or crystal habit. This is used to identify minerals that typically show well-developed crystals. They'll show well-developed crystals if there's room for the crystal to grow. We might get things like cubes, hexahedrons, tetrahedrons, and so on. Down below, you see an image of a dog-tooth calcite. Calcite, if allowed to grow, will grow into this interesting pointed feature that we refer to as a dog-tooth calcite. This, however, should not be confused with the next item on the list, which is cleavage. Cleavage is not the actual crystal form. It's not how the crystal grew, but rather refers to the breakage or splitting of the mineral crystal along one or more smooth planes of weakness within the crystal structure. This means that the crystal has been broken or fractured. If we look up above, we see a calcite crystal again. If you remember previously, we saw that dog-tooth calcite. Well, here is a calcite that has been fractured. When allowed to be fractured or broken, the mineral will actually break along smooth planes that will create a cleavage. These smooth planes, when broken, or calcite, the way it's broken, will break into rhombohedral boxes. Another example of cleavage is down here below. This is biotite. When it breaks, it actually breaks along thin planes. These thin planes are like sheets of paper being pulled or peeled apart. Well, let's look at the different types of cleavage. That first one would be like that biotite we saw, all right, or muscovite, which is another mica like the biotite, just in a lighter form. When we look at this, it peels apart like sheets of paper. We refer to it as having one plane of cleavage. Another mineral, potassium feldspar, when we look at it, will fracture along two planes of cleavage, creating two sections that are parallel to one another, that are flat planes. Another would be halite or salt. If you've ever shook the salt out of your salt shaker, you'll see that you have little tiny cubes. These little tiny cubes create three planes of cleavage. Essentially, if you were to put your fingers on the top of the box, you would have one plane of cleavage. Put it on the side of the box, your fingers again parallel, you'd have two planes of cleavage, and then on the ends, your fingers become parallel again. This creates three planes of cleavage. Halite has three planes of cleavage. Another mineral that has three planes of cleavage would be calcite. However, when we look at its cleavage, it comes in at angles that are not at right angles to one another, unlike halite, which has 90-degree angles between the cleavage planes. Another might be four planes of cleavage, like we see on fluorite. If we were to put our fingers onto the fluorite, we would be able to get it on a top crystal to a bottom crystal parallel 1, 2, 3, 4 times. We can also have crystals with 5 planes of cleavage. Let's look at another physical property. If a mineral does not have cleavage, then we refer to it as having fracture. Fracture refers to the irregular breakage of a mineral. Here we've got a quartz crystal. This is showing the quartz crystal's habit or crystal form. But if we were to zoom down into the lower corner of this crystal and look at where it's been fractured, it's irregular. This crystal has a fracture as opposed to a cleavage. Next, let's look at streak color. Streak color is the color the mineral shows in a powdered form. Here I've got a couple of examples. In the top we see that we have a mineral that's kind of reflective. It actually should look a little bit more silver than this image shows, but when it's in a powdered form it shows a reddish brown. This is a hematite. Down below we have a mineral that shows in a silverish form, galena, but when in a powdered form it shows a dark gray to black streak. Moving on, another characteristic would be specific gravity or density. The specific gravity is a way to describe how heavy a mineral actually is. Specific gravity is actually the ratio of the mass of a substance to the mass of an equal volume of water, closely related to density. However, in a classroom or at home, you probably won't try to measure the specific gravity exactly. Instead, you're just going to look at how heavy is it and record, is it very heavy or really light? This will tell you if it's really heavy, it has a high specific gravity. If it's really light, it has a low specific gravity. This would be sufficient enough in identifying the mineral. Lastly, I talked about that we had other useful mineral properties that some samples will display. For example, taste. Halite, being salt, will actually taste like salt. It can be identified by the taste. Another special property might be smell. The mineral sulfur, for example, which is a yellow mineral, will also smell like rotten eggs. Feel can also be a special property, like talc, for example. If you have ever touched talc, which is what we use for baby powder, it's very silken or soft. Double refraction is another. Calcite, if it's clear enough, can be placed onto print, and that print will essentially show as a double refraction. Another characteristic that calcite has is a reaction to a dilute version of a hydrochloric acid. When you place the acid onto the crystal itself, it begins to bubble or effervesce. What's happening is the mineral is being dissolved by the acid. As this happens, the calcium becomes dissolved and separated from the calcium carbonate becomes dissolved. The calcium and the carbon dioxide are then separated. The carbon dioxide is released as a bubbling effect. Lastly, magnetism. Magnetite is a mineral that will actually attract a magnet. As we can see in the image, we have the sample held upside down, and yet the mineral or the magnet is still attached to the mineral. Alright, so that was just a brief introduction to mineral identification and mineral properties. Once you've identified each of these mineral properties for each of these individual minerals, you can then move on to a flow chart, which you can find in many books to identify the mineral, or a mineral identification book. Using the properties you've identified, you could then use that book to identify the specific mineral in which you have. Alright, so that's the end of our presentation. Thank you and have fun.